Okay, so welcome back. And we have Mr. Guedj, who's going to give the second lecture on uniform estimated through quasi-plurisobharmonic networks. Thank you.
Thank you, Filippo. Okay, so today my goal is to explain a brand new approach to establish uniform estimates for complex Monge-Ampère equations. So let me recall first the context. So of complex dimension n, and we fix omega a semi-positive closed 1-1 form whose total volume is strictly positive. So the form is allowed it to be not strictly positive. It may vanish somewhere, but globally this integral is strictly positive. And the vague goal is as follows. If phi is a given solution of the following complex Monge-Ampère equation, then I'm going to explain that if mu is a relatively nice probability measure, then we have a uniform a priori bound on the oscillation of this function of this solution phi. So here DDC is a shorthand for IDD bar. And I'm going to recall a few properties of the class of omega personic functions and how to define the complex Monge-Ampère operator acting on them. And I will also make more precise in a few slides how nice this probability measure should be. Okay, so, and once again, the goal is to present the recent proof of this important estimate, which is elementary, so it will use far less tools than in previous proofs, known proofs, but elementary doesn't mean easy. So it's a bit tricky, but it's relatively elementary. Okay, but let me start by recalling a few important properties of the space of omega prosmanic functions. So I will denote by dvx a fixed smooth volume form. And first, as Jean-Pierre, I think, recalled briefly in his first lecture, a function is said to be quasi-prosmanic if it is a global function which is locally given as the sum of a smooth and a prosmanic function. And more precisely, I'm going to be interested in a spatial class of quasi-prosmanic functions, those function phi. So they are globally defined on X with real values, possibly minus infinity values sometimes. And since locally it is prosmanic plus smooth, in particular, it is integrable in the sense, in the Lebesgue sense. So you can differentiate it in the weak sense of distribution. So you can compute DDC of phi in a weak sense. And the constraint that we impose is that DDC phi should be bounded from below by minus omega, or alternatively, omega plus DDC phi should be greater or equal than 0 in the weak sense of currents. So the set, the class of all such functions is denoted in blue by PSH x omega. We endow this class with the L1 topology. And here is a first very important and rather simple property. If you look at the subset of those functions whose supremum is uniformly bounded in between two constants, say 0 and minus a, then this subclass is compact for the L1 topology. So as soon as you control the supremum, then you are living in a compact subset of this class of omega prosmanic function. An important property of these classes is that you can approximate them from above easily by bounded omega prosmanic functions. You can simply consider phi j, which is the maximum of phi and minus j. So minus j is a constant is omega prosomonic, the maximum of two omega prosomonic functions is again omega prosomonic, and therefore max of phi and minus j is bounded because it is bounded below by minus j, and omega prosonic, and it decreases obviously as j goes to plus infinity towards phi. So it's very easy to approximate such a guy by bounded omega prosonic functions, and it's more involved to try and approximate such a function by a decreasing sequence of smooth omega prosonic functions. It is not clear that it is always possible, but at least when omega is scalar, so when omega is strictly positive, then it follows from a regularization technique of de Mailly that this is doable. Okay, here is a spatial but very important example. So assume X is the complex projective space, CPN, and that omega is the Fubini-Study Kaehler form. Then if you consider P a homogeneous polynomial of degree K in n+1 variable, and you cook up log of the modulus of P divided by K minus log of the norm of Z denoting the coordinates Z0 to Zn. Then this function is omega prosonic for this data. And moreover, and this is a consequence of the resolution of D-bar with L2 estimates that Jean-Pierre has been telling about in his lectures, the set of such function is dense for the L1 topology in the whole class PSH, CPN, omega Fs. Okay, further properties. These classes, these functions have very good integrability properties. First of all, they are in any Lebesgue space Lm with respect to this reference smooth volume form dvx. And moreover, by compactness, if you put a bound on the supremum, then they are uniformly integrable. So the class PSHA that I was denoting on the previous slide is uniformly integrable, say, with respect to this smooth volume form for any A. More generally, if you try and integrate against a slightly more general measure mu, so you replace dvx by mu, and if PSH is an LM of mu, then by compactness again, you have actually uniform integrability. There is even a stronger property that Jean-Pierre has been using in his lectures, which goes back to the work of Skoda. So quasi-prosonic functions are even exponentially integrable with respect to smooth volume form. This is Skoda uniform integrability result. So there exists a uniform exponent alpha, which essentially only depends on the cohomology class of omega, such that the integral of e to the minus alpha u dvx is finite, and it is so in a uniform fashion if you control the supremum of u. Okay, this type of result has played a very important role in Kaehler geometry, and it has been advocated especially by Tian in the early 90s. So here is again a special example. If you take X degree D subvariety of CPN of the complex of projective space. So X has dimension little n and it lives in CP capital N, and it has degree D. Omega is the restriction of Fubini-Study to X. Then in this Skoda statement, alpha, you can take alpha being 1 divided by the dimension X times the degree of X. This would work to have this uniform integrability property. Okay, now I would like to explain, or just to say a few words about how to define the complex Monge-Ampère operator for bounded such functions. So first, from a few words about the local theory. So if U is proximonic in say Cn or you need some small open set of Cn. Then you can use standard modifiers, chi epsilon, and consider the convolution. Convolution of U with respect to such a modifier. Then what you get, of course, is a smooth function, but which is moreover pro-isomonic. So pro-isomonicity is preserved by this standard operation. And these smooth approximants decrease to U. Now, if you pick a bounded such pro-isomonic function, then Bedford and Taylor have shown in the 70s, early 80s, that the smooth complex Monge-Ampère measures DDC of U convolution with chi epsilon. They weakly converge towards a unique measure independent of the modifiers, independent of the way you approximate. And this measure has been since then denoted by DDCU to the n, so the Monge-Ampère of U. From a global perspective, if now you replace this local prosonic U by this global phi, which is omega prosonic and bounded, then you can, by using this localization and Bedford-Taylor's argument, show that the global Monge-Ampère omega plus DDC phi to the n, this measure is a globally well-defined complex Monge-Ampère measure. So if you have never seen that, it's probably extremely difficult to digest. So here is a simple example, once again. Assume X is the complex projective space, omega is the Fubini-Study Taylor form, and consider phi. So I use a homogeneous coordinate on CPN, phi of Z, is this quantity. So the maximum of the logarithm of the modulus of this homogeneous coordinate minus the logarithm of the norm of Z. So you should think that log of the norm of Z is the potential for the Fubini-Study metric. So this guy is indeed omega prosonic. And you can compute the Monge-Ampère measure of this bounded guy, and you get the normalized Lebesgue measure on RPN. Well, it's very rare that one can actually compute a complex Monge-Ampère measure. It's a highly nonlinear operator, but in this case, we take advantage of the symmetries. So you see this function has lots of symmetries, toric symmetries, and so is its complex Monge-Ampère measure. Okay, so I'm a bit embarrassed by that. Okay, so here is now a very standard operation in complex analysis and also nowadays in Kaehler geometry. This is a recipe to construct new omega prosonic functions starting from one such function. So phi is given, it's omega prosonic, and I now take chi, which is a weight, which is both convex and increasing. And I normalize this weight in such a way that the first derivative is not bigger than 1. Okay? And then my claim is that the composition chi composed with phi is again a new omega prosonic function. And the explanation is rather simple. Namely, if you compute the curvature of this new guy, chi composed with phi, then clearly you obtain two terms. Either you differentiate chi once, and then you have chi prime composed with phi DDC phi, or you differentiate it twice, and then you have this blue term. So the basic observation is that because chi second is positive, because chi is convex, so chi second is non-negative, this blue term is non-negative. So the curvature of chi composed with phi is therefore bounded from below by this quantity. So I get rid of the first blue term, and I rewrite DDC phi as omega plus DDC phi minus omega. So this gives me two new terms. And now the second blue term is again positive because omega plus DDC phi is non-negative and chi prime is non-negative. So I get rid of it. And I finally used my normalization. Chi prime is less than 1, so minus chi prime is bigger than minus 1. So in the end, I have that this is bounded from below by minus omega. Okay, so it's not a very difficult computation, but this is a good recipe to get lots of new omega pressonic functions starting from known ones. And here is a very, very special situation of that. Imagine that phi looks a bit like the log of the norm of C. Then what we are considering is the family, with this recipe, is the family of function with radial symmetries. So let me say a few words about that, because this is another situation where we can compute explicitly the complex Monge-Ampère measures. So it is actually an observation by Jean-Pierre from the, I think, late 80s, that a few years after Bedford-Taylor developed their theory, that what can make sense of the complex Monge-Ampère measures, measure DDCU to the n, not only when U is pressonic and bounded, but when U is pluriharmonic and bounded near the boundary of, say, the unit ball, or strongly bonded to the convex domain. In particular, if U has isolated singularities, which is the case if I'm considering radial symmetries. So this measure is always well defined, and I will assume here for simplicity that chi is a smooth weight. Then, so smooth, convex, increasing, and then a simple computation of first a simple observation, which will be important for us, is that clearly this function U, which is chi composed with L, well, it is bounded if and only if it is bounded at the origin, where you have the radial singularity, which simply means that the weight should be finite at the origin. Oh, sorry, there is a typo here. The weight should be finite at minus infinity. So the logarithm sends the point 0 to minus infinity. So there is a small typo here. To correct it. Okay, now a simple computation gives you a nice formula, or rather simple formula for this complex Monge-Ampère measure. Namely, so the Monge-Ampère measure of chi composed with L is, if chi is smooth, is absolutely continuous with respect to Lebesgue measure, and it is given by this density. So I also forget, I think, to say that yeah, you need to assume here for this formula to be correct that the function U does not have a logarithmic singularity at the origin. Otherwise, you would get an extra term, which is a Dirac mass. So let me assume this, although I did not write it on the slide. Then I make the following simple observation that will be important for the sequel. When is it true that pressonic functions are integrable with respect to such a measure? Well, it belongs to Lm of mu. Due to the radial singularity, the only thing you need to test is whether log of the norm of Z belongs to this Lm of mu. And well, a change of variable, so you pass to spherical coordinates and make a change of variable, tells you this is the case if and only if this integral is finite. So you have a quantitative constraint on the weight chi so that this integrability property holds true. And in particular, this will play a crucial role in the sequel. If I impose that this m, this exponent m of integrability is strictly bigger than the dimension, then this condition by integration by part tells you that chi should be finite. So once again, it should be chi at minus infinity rather than chi at 0. Sorry for the typo. And this exponent dimension strictly bigger than the dimension turns out to be critical. Because, for instance, if you consider minus log of minus t, and n should be greater or equal than 2, then I leave as an exercise to check that in that case, PSH is in ln of mu, but as you see, chi is minus infinity when t is minus infinity. So you have a log-log singularity. Okay? So these conditions will show up in a few slides, and these integrability properties turn out to be somehow critical for the a priori L infinity bound. But let me go on for a little while. Before that, and present the hero of the story of today, which is the notion of quasi-Perestrombonic envelope. So given H function on X, which is bounded, and I need to assume slight continuity property. So the appropriate property could be that one in blue, quasi-continuous. Quasi-continuous means continuous outside the peripolar set, roughly. And if you're not familiar with that, you can keep in mind that it is continuous. Just think continuous if you're not familiar with that. For those of you who are have a PD taste, H will be an obstacle. And then I consider, so H is not a priori omega Perestrombonic, and I consider its projection on the cone of omega Perestrombonic function. So I consider the supremon of all those functions, omega Perestrombonic, that lie below H. This is P omega of H. This is a classical construction in many contexts. Here are its most basic properties. First, well, because H is bounded, then P of H is well defined, it is bounded, and it is omega Perestrombonic. Secondly, if H is very regular, so C11 smooth would suffice, but let's pretend it is smooth, then the envelope is C11 smooth. So actually, I'm a bit sloppy here. Let me, just for this sentence here, assume that omega is scalar. Otherwise, one needs to be more precise about where this guy is indeed regular. So let's assume for this item that omega is scalar. And the point is that one has a very nice control on the Monge-Ampère measure of this envelope when there is enough regularity. Namely, the Monge-Ampère of this envelope is concentrated on the contact set where the envelope coincide with the function. So there is, sorry, again, a typo here. So it's pH of x equals h of x, not pH of x equals x. Sorry for that. So the complex Monge-Ampère measure is concentrated on this contact set, and actually on this contact set, it coincides with the Monge-Ampère of the function h. So let me stress maybe that the left-hand side is by the very definition non-negative measure, whereas the Monge-Ampère of h doesn't need to be positive in any sense, but the part of the statement is that the Hessian of the right-hand side is non-negative on this contact set. So the Monge-Ampère that you take is where H is omega Perestrombonic. So when H is less regular, this is no longer the case. This equality does not longer holds, but there is, with a rather light assumption, the key property that still holds, which is that if H is quasi lower semi-continuous, let's say lower semi-continuous for simplicity, then the Monge-Ampère is still concentrated on that contact set. And this is the essential property that I'm going to use in the sequel. Okay. And actually, key observation for the proof that I'm going to present lies in the following. So I take a weight, which is the opposite of what I presented before. I take a weight which is concave rather than convex. increasing still, and I take the opposite normalization. So previously I was asking for chi prime to be between 0 and 1. So the first derivative should not be too big. And here I want the derivative to be big enough. So chi prime should be greater or equal than 1. If it is so at the origin, then by concavity, it will be so in R minus, all the way down to R minus. So now I cook up, I pick some omega Platonic function, let's say it is bounded and normalized, and I consider the envelope of chi composed with phi. So chi composed with phi is no longer omega Platonic because it goes the opposite way as what I explained earlier. But I project it onto the cone of omega Platonic function, so I get a new omega Platonic function. And the observation that I make in this lemma, which is a key lemma for the sequel, is that I have a good control on the complex Monge-Ampère measure of this strange envelope. And namely, it is bounded from above by, well, the characteristic function of the contact set. This is not a surprise with what I explained on the previous slide, time the Monge-Ampère of phi, time this weight chi prime composed with phi to the n. So it's a bit, it comes out of nowhere right now, but the idea you should keep in mind is that I'm going in the sequel to make a smart choice of the weight chi. And there will be a balance between the fact that chi, because it is concave, has the tendency to push phi towards minus infinity. But on the other hand, there is a good balance with the fact that chi prime, with some luck, will decrease at minus infinity, and therefore the Monge-Ampère of the envelope is under rather good control. And putting all things together will be the key. This balancing property will be the key to establishing the L infinity estimate. So that we will see that in a few minutes. So the proof of this lemma is rather elementary when everybody is smooth. Namely, let me compute once again the curvature of chi composed with phi. So we have seen that already. We have two terms, but now the signs are reversed somehow. So when I look at omega plus dBc chi composed with phi, then the first blue term this time is negative. It was positive on the previous slide a bit earlier. Now it is negative because chi is concave. As chi prime is bigger than 1, the second blue term is negative as well. So what you get is that you have a bond from above. Previously, I was looking for a bond from below. Now I'm looking for a bond from above for the curvature of chi composed with phi. And therefore, so this is due to my normalization. And therefore, the statement of the lemma follows, because I explained that if everybody is smooth, the Monge-Ampère of the envelope equals the characteristic function of the contact set times the Monge-Ampère of this chi composed with phi guy, which is not in general omega Platonic, not always omega Platonic, but which is omega Platonic on the contact set. And due to this upper bound on the curvature, well, it gives the lemma. So you see, it's very simple as an observation. Of course, in real life, the objects I'm interested in are not smooth. So this requires some extra work, but this is not a big deal, actually. So you have to trust me on that. Okay, so now I would like to phrase in a much more precise fashion the uniform a priori bound. And we do that in two steps. First, nowadays classical setting. So let me pick a measure mu, which is absolutely continuous with respect to Lebesgue, or let's say with respect to dVx, and with a density f, which is in LP for some p bigger than 1. And I'm telling you that there is, one can then solve this complex Monge-Ampère equation. So Monge-Ampère of phi, normalized Monge-Ampère of phi is equal to f dVx. The solution is unique up to normalization, so it's more or less classical to normalize the solution by asking that this supremum is equal to 0. And the key point in this result is the following a priori estimate. Once phi is normalized by sup being 0, then we have a bound from below on phi. So the L infinity norm of phi is bounded from above by a uniform constant, which depends on essentially two things: on P, I should have said it's P bigger than 1, on the LP norm of F, and on this constant AP, which, as I explained earlier, is finite because normalized omega harmonic functions are uniformly integrable for any exponent. So here, this weird exponent n plus 1 times p divided by p minus 1. P divided by p minus 1 is simply the Hölder conjugate exponent of p. Okay, so it's, you could say it's minus u to the power q n plus 1. Okay, so this is my claim, and I'm going to explain the proof of this result. So in particular, you see that omega is not necessarily Kaehler, that you can move this statement in families, that as long as you control this constant AP on one hand and the LP norm of the density F, then you have a very strong uniform a priori estimate on the solution. Okay, so the goal is to explain from scratch a proof of this. And I'm actually going to tell you just slightly more general story, which somehow simplifies the formulation of the proof. So I'm going to consider a slightly more general probability measure mu. So here mu is f dvx. And now mu has the following, the key property that mu should have is this one. The set PSHX omega should be in Lm of mu with m strictly bigger than the dimension. And if such is the case, then once again, there exists a unique normalized solution to the complex Monge-Ampère equation, Monge-Ampère of phi, normalized Monge-Ampère of phi equals mu, with a uniform a priori bound. And here the bound depends on n, m, and an upper bound on this quantity here. So what you really need to put your hands on is this integral of minus u to the n d mu for any normalized function u. And as you can imagine, the previous result is a simple consequence of that one just by applying Hölder inequality and with m equal n plus 1. So the m strictly bigger than n in the previous result, I can simply take m equals n plus 1. Okay, so I'm going to tell you the proof of this a priori estimate. Yeah, but let me comment that essentially this statement is optimal by making the following definition. So I said that phi mu is the Monge-Ampère potential of mu if the normalized Monge-Ampère of phi mu is equal to mu and is normalized by sup equal to 0. There is something special about complex dimension 1, as is often the case, because then the Monge-Ampère is simply the Laplacian operator, it is linear. So in that case, the critical assumption is PSH in L1 of mu. So the Monge-Ampère potential is bounded if and only if you have this integrability property. But in higher dimension, life becomes a bit more subtle. As I showed you on the radial examples, there are unbounded Monge-Ampère potential if you only assume that PSH is in Ln of mu. So we need to assume that PSH is in Ln plus epsilon of mu in order to make sure that phi mu is bounded. Another comment is that in the previous theorem I stated, which essentially goes back to the work of Guedj, I was assuming that the density was in LP for p bigger than 1, but actually this type of condition would suffice. So the integral of f log f to the m with m strictly bigger than the dimension is finite. This does the job, and this had been observed already in the late 90s by Guedj. And here, this follows from my statement. If you apply Hölder-Jung inequality and Skoda's theorem, in order, if the density is like this, then you can check that PSH is in LM of mu for this m bigger than n. And maybe a comment for it's more for experts in Kaehler geometry. There has been in the last few years a very important work of Chen and Cheng towards the solution of the constant scalar curvature problem. And in their work, they use in a crucial fashion the notion of entropy. And it was perhaps unclear for some people in the area that this finite entropy condition does not suffice to make sure, to guarantee that the Monge-Ampère potential is bounded. So what I'm saying here is that if mu is f dvx with the integral of f log f dvx finite, so m is equal to 1, then phi mu has no reason to be bounded. And the radial example I mentioned earlier provide easy counterexamples. Okay, and finally, a very different type of measure, just to let you know that you can be orthogonal to the Lebesgue measure and still satisfy this assumption. If you take a real analytic hypersurface, so a real codimension 1, and you take the Hausdorff measure on it, then this integrability condition is satisfied. So such a measure will be the Monge-Ampère measure of a bounded potential with a uniform bound on the solution. Okay, so now I would like to explain the proof. How much time do I have, Filippo?
You started at 20, so I think 12:10.
Okay, I think it should be okay. So in brief words, the strategy is like this. So I'm going to focus on the upper estimates. And my plan is to show that the measure of the sublevel set phi less than minus t becomes 0 in finite time. And what I need to estimate is this maximal time t, okay? I'm going to choose in a smart way a weight chi, which is so normalized. So chi at 0 will be 0, and the first derivative at 0 will be actually 1 precisely. And I'm going to consider this projection of chi composed with phi and use the good control that I mentioned earlier on the Monge-Ampère of this projection. And the naive idea, which is a bit difficult to convey, is that the main issue is to control the supremum of this projection. Because you are pushing down with this concave function, you have your solution, you are pushing it down with composing with this concave weight. If you succeed in nevertheless getting a bound on the supremum, then you're done. That would be the story. Okay, so for the sequel, I fix a small epsilon. So I take advantage of the fact that m, this exponent m, is strictly bigger than n. So I fix a small epsilon with this property. And let me start the proof now, the real proof. I'm going to choose my weight chi in such a way, in a very precise way, so that this quantity is finite and bounded uniformly by 2. Why 2? You will see that in a minute. So let me recall this formula. I'm not sure it has a name, but if you have one in your country, let me know. If g is an increasing function normalized by 1 at 0, then you have this formula from Lebesgue integration theory, which is quite useful. So the integral of g composed with minus phi, be careful that phi has the tendency to be negative. G, I want it to be positive, so the g composed with minus phi against mu. Well, it's the total mass of mu, which is 1 here, plus the integral of g prime of t, mu of the sublevel set of phi. And I'm going to choose g, which is equal to chi prime of minus t to the power n plus 2 epsilon. This is in order to get control on the blue term above with this normalization, and I choose G so that the integral above is under control. And for that, let's take G prime being 1 divided by 1 plus t squared mu of the sublevel set of phi. If I do that, then clearly the integral above of G composes minus phi will be less than 1, which is the mass of mu, and then the integral of dt divided by 1 plus t squared. And this integral is not bigger than 1. So this could give me the bound above, the blue bound, that the total integral of chi prime composed with phi to the n plus 2 epsilon d mu is less than 2. So this is my choice. I choose G like this, and therefore I'm choosing chi with my normalization at 0. And I claim that chi has all the required property. So you see it has the right integrability property. And moreover, G prime is positive, so G is increasing, so chi prime of minus t is increasing, so chi prime is decreasing, so chi is concave, etc. Trust me on this. With this choice, chi is a concave increasing weight, which is well normalized. And well, I'm not going to give more details on that, but you can check that you have a uniform control on the value of such a weight at the point -1. Okay, now I'm claiming, so this is the choice of the weights, and I'm claiming that I can control a certain energy associated to the projection of chi composed with phi. So here is the notation for the normalized Monge-Ampère measure of this projection. And the key lemma that I explained earlier says, okay, the Monge-Ampère of this projection is concentrated on the contact set, and it's less or equal than on that contact set than chi prime composed with phi to the n times the Monge-Ampère of phi. But the Monge-Ampère of phi, by assumption, is equal to mu. So this is the control I've got. And therefore, if I integrate minus u to some small power, epsilon, against the Monge-Ampère of u, then because u is equal to chi composed with phi on the contact set, I get such an inequality. Now I use Hölder inequality. Oh, sorry, I first observe, I'm going to use Hölder inequality, but I first observe that due to concavity of chi and normalization by 0 at 0, chi is bounded from above by absolute value of t times chi prime. And then I use this and Hölder inequality to observe that the energy of u, the epsilon energy of u, is bounded from above by the product of two terms. So on the right-hand side, I have this weird integral of chi prime composed with phi, but this quantity was bounded from above by 2 on the previous slide. And the first term here is precisely this constant am mu raised to the power epsilon. Okay, so to sum up, with my choices, what I do get here is that the projection u has an epsilon energy, which is uniformly bounded from above. And this gives me a uniform control for the supremum. Namely, the minus the supremum raised to the power epsilon is certainly equal to the integral of that guy, which is less than the energy, just bounded from above minus u by minus u. And this, I explained, this was bounded from above by 2 am to the power epsilon. Therefore, U belongs to this class PSHA, which I told you at the very beginning is a compact subspace of L1. So because U has this property, well, then I know that such an integral is uniformly under control. But on the other hand, minus U is more singular than minus chi composed with phi. I therefore get a control on this of integrability for minus chi composed with phi. So what do I get at the end of the day? This last information, if I use Chebyshev inequality, tells me that the sublevel set of phi decrease with respect to mu in a certain fashion. On the other hand, I have chosen the weight chi so that this sublevel set decreases with respect to mu in another fixed fashion. So I have two pieces of information. I now collect them all together on the next slide. So let me change slides. I also change notation because there are too many minus signs. So let me introduce H, which is the positive counterpart of chi. So H is defined on the positive rails, and H is convex increasing while chi is concave increasing, and the normalization are here. And then G was chi prime of minus t, so G is H prime of plus t to the power n plus 2 epsilon. You can differentiate G prime. And the information that I was finishing by at the bottom of the previous slide is this type of inequalities. So let me rearrange them. I multiply by H prime, and if you put everything together, this is the piece of information that we have obtained. With the choices we have made, we have this differential inequality in blue. You can, that's the reason why I multiply by H prime, you can integrate on both sides. On the right-hand side, you have this term 1 plus t squared, which is somehow not the most important. So I simply bound from above 1 plus s squared by 1 plus t squared if s move in between 0 and t. And what I do get that way, rearranging the inequality is something like that. And you see the key point here is that on the right-hand side, the power of h is bigger, the exponent in the power of h is bigger than that in the power of h prime. And on the other hand, on the left-hand side, you have power 2, which is strictly smaller than n plus 2 epsilon plus 1. So I can rewrite this inequality like this, 1 plus t to some small power, small negative power less than 1, is less than c h prime divided by h to some power bigger than 1. I can finally integrate this between 1 and t max, use my lower bound for h, and obtain a uniform upper bound for t max. So you see, the only somehow deep tool here is this projection, and the rest is a tricky way of choosing the weight. But the whole proof is here. So you have essentially everything you need to know in order to get this uniform estimate. Oh, so to conclude, let me mention that one can push this method in various directions. So first, a slight extension of the method allows to handle the case of big homology classes in a slightly different direction. You can get stability estimate and proof continuity of the solution with the same type of extension. You can handle degenerating families. So if you are looking at families of Calabi-Yau varieties or families of Monge-Ampère equations in various geometrical contexts, then this uniform Accurate estimate is so somehow under control that you can follow up the uniform estimates in families. And slightly more involved, but important too, if you are interested in solutions that are not globally bounded, but rather locally bounded in the complement of divisor with a sort of uniform control on the blowing up behavior in the divisor, this is a type of a priori estimate that have been developed by Wang-Qing Lu and Eleonora Di Mezza a few years ago, where this can be also achieved by this exactly the same method. And as you've seen from the proof, there is, for the people who are used to pluripotential theory or Kaehler geometry, I have not used a single integration by parts. So this is a good sign that this method actually extends nicely to the case of Hermitian geometry, where the pluripotential or more traditional pluripotential techniques rely very heavily on the fact that the form is closed. And here you can actually reach the case where the form is not closed because, well, essentially I'm not integrating by parts. So there is no error terms that will come up here. So of course there are other sources of difficulties, but that's another story than what I can say today. Okay, so this is what I wanted to say. And I just finished by mentioning a few references. So after Yao's fundamental result from 78, proving the L infinity a priori estimate by Moser iteration process, so by a rather different method, the first breakthrough was done by Guedj in 98, where he proved this uniform a priori estimate by pluripotential techniques. His method has been a bit extended in the previous work with Philippe Sidieux and Ahmed Zeriai. There has been an alternative interesting proof by Brodsky that still uses pluripotential techniques, but more from a local perspective. And what I've been explaining today to you is a part of a joint project with Wanqing Lu. And we have just posted on the archive this morning the first two parts of this project. I was hoping that the third part would be ready for this workshop, but we are polishing this third chapter, so this should be available in the coming weeks. Okay, I'll stop here and thank you for your attention.
Thank you very much, Vincent. Thank you. Okay, there is a question in the chat.
Yeah.
Can you see it, or I can read for you?
I'm just about to see it, yeah.
Yeah.
So the proof somehow is, by definition, I don't know what is the best way to answer. What we get at the end here is that by definition, mu of the sublevel set is 0 if T is bigger than T max. So the point here is to you can work a priori. Say you can even think that phi is a smooth solution. So you know it is bounded. What you want to prove, so you know that mu of phi less than minus T is 0 at some point, after some point, and this point is the infimum of the solution. Okay. So what you want is to estimate this infimum that I'm denoted in the proof by T max, and the differential inequality that I'm integrating tells you by the very end of the proof that you have a uniform bound on this T max. So I'm not sure I'm answering correctly your question, but if you like, in the whole process, you cannot make sense of this differential inequality if you are dividing by 0 or blowing up at each step. So you analyze this differential inequality on the interval 0 up to T max, and then you do the work.
Okay, other questions? We have, I recall you that we have maybe we take 10 minutes break, then there will be the question and answer session with Vincent. So if you have a more general question, maybe we can postpone to this time. Otherwise, if you have a specific question, you can ask. Okay, so if this is not the case,